Lab 1, Newton's second law on constant velocity. Our hypothesis states that the video is going to show an object with constant velocity, i.e. the final velocity is equal to the initial velocity. We have a video showing the motion of a toy car with accompanying graph and the data points. Here's our toy car driving in the negative x-axis. You'll see on the right hand side our fairly linear chart going in the negative x-axis. You'll see here we have our points for time and location, and we utilize those first 2 points to come up with our initial velocity. Next, we're going to show you the Python code showing how the model equations were derived to come up with our model graph. You'll see that the mass of the ball is entered in at 0.044 kilograms, our scientific units. The initial position of the ball is going to be at a vector of 0, 0, 0. We also utilized the change in position, as I stated before, the first 2 frames of the video and the corresponding times to get the initial velocity of the ball, or in this case the car. VI equals delta R over delta T. You also notice that the delta T is 0.005 seconds. We utilize as a fairly small time frame because the video is only 12 frames, and at 30 frames per second that's quite short. So we wanted to use a delta T that was sufficiently small to correspond with that. However, because we are using a constant velocity here, we know that the net force divided by the mass multiplied by delta T is always going to equal 0. Therefore, it does not actually matter what the delta T is in this case. We could have made it quite larger, knowing that we are multiplying out by a factor of 0. We would have been just fine. Next, we're going to scroll down to the while statement showing the time overall at 0.4 seconds. Once again, we go to our net forces which are acting on this model. They're going to equal 0 in all axes, the x, y, and z. We also see the Newton's second law written out in Python code. We remember that because we're having a constant velocity, that the F net divided by m is going to equal 0. And once again, therefore, delta T size does not make a significant difference in this experiment, or in this model, I should say. And then we get our position of the ball. It's acquired by adding the velocity multiplied by the change in time, and add that to the current position, and our increment for the while statement. So now we're going to run our model, and we will see that it appears that the line of the model goes in the same x-axis direction as our video, in the negative x-axis, which is good. And we see also that our progression looks linear here, going from the 0 time and in the negative x direction. Now we'll see our comparison of our experimental data versus our model data, see how they correlate. Here are the graphs. You'll see the red line shows the model position, very linear, showing that constant velocity. And you'll see then the blue dots showing the experiment position. You'll see that they kind of trail off near the end of the time frame. If you ignore the first few plot points, you'll notice that the progression of the blue dots looks linear from point 3 all the way down to the last experimental point. What this says to me is that the video taken did not show the car while it was at its constant motion, constant velocity. It actually showed it accelerating and then reaching its constant velocity by the third point or time, 0.1 second. What if the axes were flipped? Well, let's take a look by flipping the x-axis. We'll do that by changing the value of the x component of the vector from a negative to a positive, thus flipping the x-axis over the y plane. We'll run this module, and we will see that the ball actually goes in the opposite direction now as it did in the original module running, And we will also see that the angle of this line goes in the positive direction as opposed to the negative direction. The flipping of the axes has no change on the magnitude of the vector, but changes the direction of the vector. The forces that were in play during this experiment were the force of the push, gravity, the Earth's gravity, primarily, the force of friction, and the force of drag. Our conclusion states that the video showed a reasonably good fit for constant velocity. Ignoring the first two data points as showing acceleration rather than constant velocity, we see that there's a good linear fit for the remainder of the points.